Hello YouTube. So I wanted to have a brief look at infinity. In modern mathematics there have been a number of very interesting results on infinity, and I just wanted to present some here. You don't need a technical background to understand the stuff I'm going to talk about. I'm going to do this in a completely accessible way, but this is just some of the modern mathematical thinking on infinity. So let's get started. The first thing I wanted to discuss is a thought experiment created by the mathematician David Hilbert, known as Hilbert's Hotel. Suppose we have a very big hotel, a hotel that's so big it has an infinite number of rooms. So there's our hotel here, and we have our rooms going on for infinity. And now suppose that one day an infinite number of people come to stay at the hotel. They have very good business, this hotel. So you have an infinite number of people at the hotel. Every room is occupied. Well, the question is, what happens if somebody else comes along and wants to take a room? Can the hotel accommodate him? Intuitively, it looks like every room is occupied, every room is occupied, the hotel is full, but might there nevertheless be a way of accommodating this person? Well, in fact, it's actually quite easy to make room for him, and here's how we do it. What we do is we simply take the person in room 1 and move them to room 2. We take the person in room 2 and move them to room 3. The person in room 3 moves to room 4, and so on, all the way down the line, and that should open up room 1. So more formally, what we're doing here is, for every room n, the person occupying n moves to n plus 1, where n just represents any arbitrary number. So for any room number, take that room number and add 1 to it, move the person to that room. And this will work because there are an infinite number of rooms, which means the rooms never end. So even though the hotel was full, there will always be a room n plus 1 for the person in room n to move into. And take any number, take 1 billion, 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 whatever you like. Okay, well, take that number. You can always add 1 to it. So there'll always be another room for the person to move into. And so if you do that, then that frees up room number 1, and we can simply put our newcomer in the unoccupied room 1. And so what this seems to show us, at least intuitively, is that if we take infinity and add 1 to infinity, then we get infinity. Now it's important to note with this example, with what we've done here, that it wouldn't work the other way around. We couldn't have just sent our newcomer to the end of the hotel, because there is no end. The hotel goes on forever, and in any case, every room is occupied. And yet, nevertheless, if we're smart, we can still make room for him by sort of putting him at the start, moving everyone on 1. So that's one person added to our infinite hotel. But now suppose that instead of just one person needing a room, an infinite number of people turn up wanting a room. So again, we've got our hotel, and every room is occupied. We have an infinite number of rooms, an infinite number of people occupying those rooms, and then an infinite number of people turn up wanting a room. Can we accommodate them? Well, here, again, we actually have a very simple solution. What we do is we take the person in room 1 and move them to room 2. Okay, then we take the person in room 2, move them to room 4. Then we take the person in room 3 and move them to room 6. So what we're doing is we're doubling their room number. The person in room 4 would move to room 8, the person in room 5 would move to room 10. So generalizing, for every room n, we take the person occupying n and move them to 2n, that is n times 2. So we just multiply their room number by 2 and move them into that resulting room. So what this means is that all the even numbered rooms will be occupied, but all the odd numbered rooms will be made available, and our infinite number of people can be moved into the odd-numbered rooms because there are an infinite number of odd-numbered rooms. And so we can easily accommodate our infinite new guests. And what this sort of seems to show intuitively is that if we take infinity and then add infinity, we end up with infinity. Okay, now this final example is a little more tricky. This time we have our hotel and it's full again, but this time it's visited by an infinite number of buses, right? So we have our Hilbert's Hotel, it's all occupied and it's visited by an infinite number of buses. And each bus contains an infinite number of people. They're very big buses. So again, we have our original hotel, there's an infinite number of people in it, and then it's visited by an infinite number of buses, and each bus contains an infinite number of people. How is the hotel supposed to make room for all of these? This, it seems, may be just too much. Well, as a matter of fact, there are actually various different ways of dealing with this problem, but I think the easiest to understand is one that's called the interleaving method. Here's what we do. We assign a number to every bus, and we assign a number to every seat on every bus. We just imagine that the hotel is bus 0. So here's our hotel. We just imagine the hotel is another bus, like any other bus, and that its rooms are seats. And this is our hotel, which we've numbered 0, and we've numbered the rooms in the hotel as they were numbered before. And then we have all the other buses. So here's bus 1, bus 2, bus 3, and they have their rooms, their seats numbered 1, 2, 3, 4, 5, and going on down. Here's what you do. You take the bus number and take the seat number, and if either number is shorter, add zeros to it until they're the same length. So for example, you might have somebody from bus 12, seat 4892. Well, in that case, you add zeros to the 12, so you've got 0012 and 4892. Okay, then we interleave these digits. Bus, seat, bus, seat, bus, seat. So we have 04081923, like that. They're interleaved. Now, we chop off the first 0, so that we have this unique number, and we send them to that room. And as long as we interweave them like this each time, the same way each time, bus number, seat number, bus number, this provides a method for assigning each passenger a unique room number. Just think about it. No person will have the same bus number and the same seat number. Some will have the same bus number and some will have the same seat number, but no two people will have the same bus number and the same seat number. So by mixing the two numbers like this, we can generate a unique number for every person. And that means that we can accommodate them in our hotel. And this seems to show that infinity multiplied by infinity is also equal to infinity. Okay, so those are the sort of three things to do in Hilbert's Hotel. And there are a couple of morals to take away from this. Firstly, infinity might be a difficult concept, but it's actually not an impossible concept. Prima facie, humans can grasp infinity, we can operate on it, we can make inferences from it, and we can do things with it. Secondly, it seems that no matter what we do to make infinity bigger, we end up with infinity. And conversely, we can take things away from infinity and still have infinity. Infinity minus 1 is infinity, infinity minus a million is infinity, and so on. So it seems that we can show that all infinities are the same size. Well, Hilbert's Hotel is an excellent way of motivating thought about infinity, but let's try to define with a little more precision how infinity works mathematically. And for this, we need some very basic set theory. So set theory. Well, I'm going to introduce the concept of a set. And putting it in very simple terms, a set is just any collection of objects. And we denote it using these curly brackets. For example, there's a set containing 0, 1 and 7. There's a set of all apples. and this sort of notation here is read: the set of all x's such that x is an apple. So that just denotes all apples. There's a set containing Frank Zappa, the smallest rat, and the set of all apples. So sets can include other sets. We call the things that make up a set its members or its elements. So Frank Zappa is an element of this set. The number 0 is an element of this set. The apple I ate this morning is an element of the set of all apples, and so on. Now, any collection of objects can be a set. In this video, we'll mainly be concerned with sets of numbers, obviously. We also talk about subsets, and we say that the set A is a subset of the set B, just in case everything in A is contained within B. So every element of A is an element of B. So if we had a set containing just, for example, 0 and 1, well, that would be a subset of the set 0, 1, 7. Fairly simple. On this definition, of course, every set is a subset of itself, because obviously every element of the set A is an element of A itself. Okay, we also talk about proper subsets. And a proper subset, well, the set A is a proper subset of set B, just in case every element of A is an element of B, and B contains at least one element that's not in A. For example, the set containing 1 and 7 is a proper subset of 0, 1, 7, because the latter contains all the elements that the former does, plus something else, namely 0. The set of all green apples is a proper subset of the set of all apples. I think that's fairly simple. And of course, intuitively, a set couldn't be a proper subset of itself. Now, the question is, what does it mean for one set to have the same number of elements as another set? Well, this might seem like a silly question, but we have to be precise. So what does it mean to say that? Well, we can show that one set has the same number of elements as another set by placing each of their elements in one-to-one correspondence. So for example, what does that mean? Well, let's take the two sets we saw earlier. 0, 1 and 7 is one set, and then the other set, it contains Frank Zappa, the smallest rat, and the set of all apples. Well, the point is that we can pair off each of these elements one-to-one, like this. So we can pair off 0 with Frank Zappa, we can pair off 1 with the smallest rat, we can pair 7 with the set of all apples. And as you can see, we have nothing left over in either set. We've paired them up one-to-one, and each set has nothing left over. They're both the same. So that's one-to-one correspondence, and that quite clearly shows that's an actual clear, precise demonstration that each of these sets has the same number of members. Now, obviously, these sets contain completely different kinds of things. That doesn't matter. All that matters is that we can pair them off somehow. It also doesn't matter sort of in what order we list them. We could have put 7 up here and 0 down here. That doesn't matter. All that matters to this point is that we can pair them off. We can pair off each element one-to-one. And as long as we can do that, then we've shown that each set has the same number of elements. Each set has the same size. Now, in mathematics, the size of a set is given by its cardinal number. And the cardinality of both of these sets is 3. The cardinal number just measures how many elements there are in the set. It's simple stuff, I think. Okay, so now let's consider the set of natural numbers, going on from 1 to infinity. And now what I want to do is, let's remove half of these numbers. Let's remove the odd numbers, so we end up with just the set of even numbers. So we've just taken this set of our natural numbers and removed half of its elements. And yet, we can easily place these sets in one-to-one correspondence. You see, although you might think, well, we've just removed half of the members of this set, so our set of even numbers must be smaller. In fact, the set of even numbers goes on forever, so you're never going to run out of them. So you can always pair it off with the natural numbers. That's quite a surprising result, perhaps. It seems to violate what we know about equivalence. We can take the natural numbers, remove half of them, and end up with something that's still equal in size to the natural numbers, that still has the same number of members. But infinity is a strange thing, and this one-to-one pairing shows that they must be equal. As far as I'm aware, this unusual property of the natural numbers was first demonstrated by Galileo. Anyway, what this means is that when we're dealing with infinite sets, some of the proper subsets of an infinite set can be the same size as the whole set. In fact, this consideration led to a famous definition of infinity given by Richard Dedekind, which is that a set is infinite if and only if it can be placed in one-to-one correspondence with one of its proper subsets. That is, you can take the set, remove parts of it, even infinite parts of it, and end up with a set of precisely the same size. Remember that A is a proper subset of B, just in case every element of A is an element of B, but B contains more than A. Clearly, if we're dealing with finite sets, a set could never be placed in one-to-one correspondence with one of its proper subsets. The original set would always contain more. But actually, when we're dealing with infinite sets, that isn't the case. It can be shown to have the same size as one of its proper subsets. So, the set of even numbers can be paired with the set of natural numbers. What about the set of integers? In this case, we have the number line extending both ways, and we're sort of trying to add more to the set. Of course, given what we saw in Hilbert's Hotel, that should not really suggest to us that that would be a problem. And it turns out that it actually is very easy to pair these with the natural numbers. All we have to do is take each positive integer together with its negative counterpart and then simply list them in a line like this. We've got 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. And then it's obviously easy to put them in one-to-one correspondence with the natural numbers. It's just like that. So there we have it. There's the even numbers and the integers. Well, what about the set of rational numbers? Rational numbers are the numbers that can be expressed as fractions, such as 1/2, 1/3, 6/27, whatever. Now, an interesting property of rational numbers is that between any two rational numbers, there's an infinite number of other rational numbers. For example, suppose we take 1/3 and 1/2. Well, these are equal to 4/12 and 6/12 respectively. But between 4/12 and 6/12 there is 5/12. Okay, so take 4/12 and 5/12. Well, 4/12 is 8/24 and 5/12 is 10/24. Between these is 9/24. And this kind of thing could continue indefinitely. In general, it's easy to see that by taking any two rational numbers, you either find a common denominator, or if they already have the same denominator, double it, and in that way you can easily find a new rational number that lies between them. So we've not just got infinity along a line here, we've also got infinity in the other direction, as it were. That between any two numbers on our line, we have an infinite number of other numbers. So it seems that this might be a bit of a problem, that we're sort of dealing with a new degree of infinity. Well, it turns out that there's a way to get even the rational numbers into one-to-one correspondence with the natural numbers. Suppose we lay out the rational numbers on a grid, like this, and we've got 1 over 1, which is just 1, half, third, 1/4, so on, and then going down this way, and we've got all of our rational numbers here. Well, we can work across the grid in this fashion. we start from 1 over 1 and go to 2 over 1. Then we go up to 1 over 2, then across, and then we go down diagonally, and then up diagonally, and we go in these diagonal lines indefinitely along our grid. Now obviously there are repetitions there which we can just delete, and then we write out what we go through in a list. So like this. So we start from 1 over 1, then 2 over 1, then 1/2, then 1/3, then 3 over 1, then 4 over 1, 3 over 2, 2 over 3, and so on, all the way to infinity. And in this way, we will have found all of the rational numbers. We will have listed all of the rational numbers, and this allows us to pair up every rational with every natural number, like that. So even though we seem to be dealing with another degree of infinity, it turns out that even these can be paired up if we're smart about it. We can find a way to list them, to put them into one-to-one correspondence with the naturals. There's an intuitive sense, I think, that infinity is as big as can be. That no matter what we do to infinity, no matter what we add to it or take away from it, infinity remains the same. And the examples that we've seen so far have provided a great deal of mathematical support to our intuitions. Well, now I want to introduce an argument that really smashes those intuitions. And this argument was published in the 1890s by Georg Cantor, a mathematician, and it's a wonderfully simple argument. It doesn't require any technical background, but it establishes a truly surprising result, namely that there actually seem to be different sizes of infinity. Some infinities are bigger than others. This is Cantor's diagonal argument. So we've seen that the set of even numbers, the set of integers, and the set of rational numbers can all be placed in one-to-one correspondence with the set of natural numbers. So these sets all have the same size. Now let's consider the set of real numbers. The real numbers include all the numbers we've seen so far, plus the irrational numbers. And irrational numbers are numbers that cannot be expressed using a fraction. They have an infinite number of non-repeating decimals. The square root of 2 is one of the most famous ones. Another is pi. These numbers have an infinite number of decimal places, and they don't repeat. There's no sort of pattern to it. They just go on to infinity, non-repeating. We can't put them in fractions. So the question is it possible to find a way to place the real numbers in one-to-one correspondence with the natural numbers? Well, let's suppose that somebody's found a way to do this. So we'll imagine, for the sake of argument, that somebody has done it. They've found a way of placing the reals in one-to-one correspondence with the naturals. If they have indeed found a way to do this, then they can produce a list like the lists that we've seen so far. They can produce a list on which we have all the real numbers paired off one-to-one with the natural numbers. Now, in order to simplify this, I'm going to focus on just the irrational numbers between 0 and 1. So, just the irrational numbers between 0 and 1. These are 0 point such and such, all the way into infinity. So this purports to be a list of all the irrational numbers between 0 and 1, paired off with the natural numbers. Now here's what Cantor does. He says, right, I'm going to make a number now. It's another irrational number between 0 and 1, so it starts with 0 point. Now in order to build the rest of it, I'm going to take this list, and then I take the first digit of the first number after the decimal point, so the first digit here of the first number, and add 1 to it, so 7 becomes 8. Then I take the second digit of the second number and add 1 to that, so 4 becomes 5. I take the third digit of the third number, it's 2, it becomes 3. and the fourth digit of the fourth, that's a 9. So instead of writing 10, we'll just put that back down to 0, so the 9 becomes 0, and so on, all the way down the infinite list. We go down the list diagonally, adding 1 to each digit to make our number. Now what we have here is an irrational number between 0 and 1, so it should be on that list, but it can't be on the list. We've constructed this number by working through the list and changing a digit of every number on it. This new number must differ by at least one digit from every other number on that list. Just think about it. Look, it can't be the first number because it's different in the first place. It can't be the second number because it's different in the second place. It can't be the third number because it's different in the third place, and so on. For every number n, it's different in the nth place. Now, obviously, we could just say, well, hey, let's just add that to our list. That would be quite clearly futile, because we could just do this process again and create another new number. No matter how many new numbers we add to our list, we just can't list them all. We can keep creating new ones. So what this means is that the real numbers cannot be placed in one-to-one correspondence with the natural numbers. Our sets must have different sizes. Further, since the natural numbers are a proper subset of the real numbers must be bigger than the set of natural numbers. Both the natural numbers and the real numbers are infinite, but the infinity of real numbers is bigger than the infinity of natural numbers. So some infinite sets are bigger than others. In order to express the different cardinalities, mathematicians use what are called the Aleph numbers, and the infinity of the natural numbers has cardinality Aleph null, which is written like this sort of squiggly n with a 0. That number there represents the size of the infinity of the natural numbers, the size of the set of natural numbers. And the next biggest infinity has the cardinality Aleph 1, which, again, that should be a squiggly n, but I don't have that symbol on my computer, so I've just got n1. It's very controversial whether the infinity of real numbers should be labelled Aleph 1. So that basically the question is, are there infinities bigger than the natural numbers but smaller than the real numbers? If so, then the reals are bigger than Aleph 1. If not, then the reals are Aleph 1. This is currently undecided. Another question is, are there infinities bigger than the real numbers? Well, it turns out that yes, there are even bigger infinities than this. In fact, there are an infinity of infinities. The Aleph numbers continue on forever, like that. I'm not going to demonstrate any of that. That's more technical stuff. But this does mean that whenever you engage in the I'm the best times infinity, I'm the best times infinity plus 1, I'm the best times infinity, those sorts of arguments, whenever you engage in those, as cultured people are prone to do, you can in fact one-up the opponent by pointing to the Aleph numbers. Certainly Aleph 8 is much, much bigger than the infinity that we would usually think of. Okay, that's all I wanted to talk about here. That was a sort of basic exposition of the modern mathematical consensus on infinity. Of course, infinity in general is a far more broad concept, and it has a rich history that's well worth exploring. But that's all for today. Thanks for watching. Goodbye.